So I want to give you in the next 20 to 30 minutes an overview of the ReMaP project, of the ReMaP platform, and how I think it can be useful for the Pathfinder project as a whole. So I followed the structure that Leah has given for these talks. So she made a nice template, and Marius used this last week to present the Nexus project. So some of those slides are following this structure, and in between I fit my own stuff on ReMaP. So let's start with the purpose. First of all, ReMaP stands for Renewable Management and Real-Time Control Platform. And if there's one thing that you should take away from this, is that it's about control. It's about controlling assets in the future energy world, which will be much more interesting, much more demanding than it is today. It is about development, experimental validation of these control algorithms and also of hardware components. And the thing about ReMaP is that there's a simulation side and there's a hardware side. So what we call the simulation framework and the control framework, which controls really your hardware components. And the key behind ReMaP is that we want to offer a seamless transition from a pure simulation, something you could call a digital twin, to partial experiments embedded in simulations, so partial hardware components embedded in simulations, hardware in the loop, eventually to a full experiment. And we interface to existing research platforms, which is the ESI platform at PSI and the eHub platform at EMPA. We also included things, so elements, hardware elements at ETH, and we are open actually to include more into the future. The partners of the project, I mentioned the two main ones, EMPA and PSI, and there's a couple of more that are contributing to various aspects of the project. You can see it on the bottom right. The key behind everything is we want to minimize the risk of directly going to a real life demonstrator. So this is a kind of a controlled environment where you can try out things. So the motivation is that the future is more complicated than the past. It sounds like a trivial statement, I'm sorry, but in the old world, to satisfy our demand for electricity, heat, and mobility, it was relatively simple. Heat was satisfied by fossil oil and gas, and actually we had an oil tank in the simplest case. There was no control necessary. The oil tank was filled once a year, and then we turned the burner on when we needed heat. In the case of mobility, it's also pretty simple. The primary energy is put into a tank, and you can do this whenever you want. There's no problem really with this. The energy services are completely decoupled. In the new world, we have fluctuating power generation. First of all, there's a lot of photovoltaics that will be there, and the energy services are tightly coupled. Heat is coupled to electricity via heat pumps. Mobility is coupled to electricity via electromobility. And we have storage elements that we can add to that. The heat storage, in case of mobility, vehicle to grid, grid to vehicle. There's also H2 electrolysis, where we can buffer then the hydrogen in a hydrogen tank. So the energy servers are very tightly coupled. And those new devices, they allow for flexibility. That's good, they allow for something, but it's also not easy to control them. And that is exactly the playground where ReMaP is active. This new world where everything is interconnected. Just one slide to show you a little bit how this world could look like. These are results from our joint activity scenarios and modeling, which I did the last 4 years. This shows a typical year with 24 days, electricity generation and heat generation. You can see here the spikes of the photovoltaics. So that goes from winter over summer to winter. And you can see the reaction that's pumped hydropower stations, industrial heaters, heat pumps that react to this, and they may charge electrical, they may charge thermal energy storage. You may produce hydrogen, store it in a buffer tank, and later on turn it back to electricity. Everything is complicated. Everything goes up and down. It fluctuates and so on. And that is a challenge that we have to address in the future. Now, what is the scope of ReMaP? I want to place it actually in a development from the lab scale, where you develop the concept, where you make maybe a theoretical analysis, you may do small scale lab experiments, to the real life demonstration of pilot and demo projects that, of course, eventually we want all to get to, also within the Pathfinder project. So ReMaP is somewhere in between. It's pre-industrial pilot and demonstration. So it's a demonstration of new control concepts or hardware component at an intermediate scale. That's where we have placed ReMaP, and that's where we want to continue working with ReMaP in the future. So Let me explain what the ReMaP platform really is. Sounds very abstract what I said so far, so let me try to fill it a bit with life. There's a software side, and that's all based around something that we call the simulation framework. Simulation framework is a highly modular software tool based on Python, which is developed at the Forschungsstelle Energienetze of ETH. So there are component models for various things, and I just listed a few, the typical ones, but the three dots here stand for all the others that I didn't list here. There are control models, PID, model predictive control, whatever, and there's an archive for demand, for generation data. So these things together, they build what you call the simulation framework. That's all software. Then there's the control framework. The control framework is the interface to the real world. And the real world in this case is not the real world like a city or so, but it's those hardware platforms that have been built in the past years at PSI, that's the ESI platform, and at EMPA, which is the EHA platform. And then I added here also other platforms, which is, for instance, the CHP plant at ETH, which I will talk about in a minute. The control framework interfaces with those real life platforms. And that's all based on a software that is based on the Venius platform that is developed by our partners, Supercomputing Systems and Smart Grid Solutions. So these two together form the ReMaP platform. So, and what I said before, what we want to offer is a seamless transition from a purely software-based approach where we build a digital twin of a system that we're interested in, and then we can turn it over to the hardware via the control framework. So let me give just one example. Let's take a very simplest case that many of us have maybe looked at one day. It's PV generation. There's a battery, there's a heat pump and a thermal storage, and those together have to satisfy a demand for electricity and for heat that is somehow given. And there's a generation profile for the photovoltaics that is also given. It's taken from the archive. And now somebody has a nice idea for a new, whatever, model-based control algorithms to control the thing. So he's setting all this up within the simulation framework, using modules that are already existing, or maybe adding his own modules, because it's a very modular approach. Once he is satisfied with the performance of his new controller and of the models that he has generated, he can decide to now move some of those components to the real world. So what I showed you symbolically, the heat pump is now the real heat pump of the EHA platform. The thermal storage is also the real thermal storage. The photovoltaic is here. And now for whatever reason, it's just a made up example, there's no battery available. So the battery we simulate. The battery stays actually on the left side here within the simulation framework. Now we can run the overall platform and simulate the battery and have all the other things operating in real life. That's what we call hardware in the loop. So this is the idea behind this. And I mentioned, I didn't mention before, but there's three boxes here that I didn't talk about yet. This is your new component. So I'm talking now to people who may be interested to use this, also our industrial partners. There may be your new component or your new controller that we want to try out, and which could also, they could live on the software side, they could live on the hardware side. So it's completely open with things that we want to add. It's always possible to add due to the software architecture that we have chosen. Now I want to walk you through three examples of what we did within ReMaP, what we are doing within ReMaP. One of them we have executed already. The other one is what we are doing now and what we will do in the next 1.5 years until the project is still running. So the first example is actually a combined heat and power plant. I call it case number 1 here. The project objectives at the time were to develop and validate a control strategy to improve the flexibility and to decouple heat and electricity production. So it's a classical case where you have a CHP plant, a combined heat and power plant, where you have an engine that produces electricity via a generator, at the same time produces a lot of heat. And it may want to supply both electricity and heat at the same time. But the problem is they are not always, you don't need both obviously at the same time. That was work done by Philipp Buchecker, Christian Schürch at ETH. So how we did this is, there's the CHP plant. The CHP plant was a real plant. at the LAV Institute at ETH, there was a demand data, which was actually also real demand data at the Nest building at EMPA. Then there was a controller that was, of course, a piece of software sitting within the simulation framework. And the thermal energy storage, well, there was no real thermal energy storage. The model was also sitting within the simulation framework. So real hardware components and the controller and the simulated thermal storage. And what was done now, this is just one example. It shows electrical power. This is thermal power. This is the level of thermal energy storage. The controller decided at some time to turn on the plant to deliver electrical power, because in this case, it's a simulated example, of course, because it decided that it's commercially interesting now to produce electricity starting here at 7 o'clock. At that time, the demand here, which is the red curve, the demand for thermal power was higher than the production, and this was taken from the thermal energy storage. But then once the electricity produced, the thermal power output of the plant increased as well, and it pretty quickly went over the level of the demand, which is a red curve. And as a consequence, the level of the thermal energy storage increased until a point here at the evening, or no, not at the evening, 2 hours later, where the plant turned off. And from this moment on, the demand can again be satisfied from the thermal energy storage. So these were real things happening really, and this was simulated, the thermal energy storage. That's one of the examples how these things can work together. So that is something that we have shown actually in December last year. And now let me give you one other example of something that we are preparing right now. This is about a charging station at a highway. So think about you have an electric car that wants to charge. You have PV production, of course, as usual, fluctuating, so it doesn't really fit to the demand of your car that is coming here. Now you can have a battery to buffer this, a big battery that is sitting there on at the highway, or you may have a system with electrolysis, a hydrogen tank, and a fuel cell, which would have the advantage of a larger, where the storage volume is decoupled from the power. So that is an example where we work with where PSI is in the lead. Markus Oberst, Tilman Schiltau from PSI are running this here. And the objectives again to validate the control strategy and to also understand really the interplay of the various components. So this is a case where the real hardware components are the battery, actually sitting at EMPA, the electrolysis and the fuel cell sitting at PSI, where to my best knowledge at the moment, it's not completely clear whether the fuel cell will really be operational. And if it's not, we will again replace it by a simulated fuel cell. And the hydrogen tank is simulated. The hydrogen tank doesn't exist really, and also the demand here and the production from the photovoltaics will be simulated. This experiment is being set up now, and we plan to run it using the ReMaP platform during June, probably latest in July. That's case number 2. Case number 3 is a bit more abstract, but I like it a lot because it's very much about the key of ReMaP, which is about control. So it's called the real-time state estimation and feedback optimization of electrical distribution grids. This is work by Miguel Picalo Cruz and Florian Dörfler from ETH. And it's about developing new control strategies really for distribution grids. So there's the challenges, which is the integration of renewables. Of course, we know there's a fluctuating generation. Then also new modes of using electricity, which would be electric charging vehicles, for instance. So it's decentralized, two-way power flows, unpredictable generation, and so on. On the other side, the world has changed, and not only on this side, it's also changed on the other side. We have a lot of sensor and communication equipment that we didn't have in the old days when an electricity system was basically controlled at the lowest level simply by the big rotating masses of the hydropower and nuclear power plant and coal power plants. So we have all those assets available, which allow for an end-to-end real-time monitoring, control, and optimization. Now there's two different worlds, really, how the energy system is being operated. There's a slightly longer term view maybe, or usually hours to days, which is a feed forward planning, which is an optimization where you dispatch your assets a priori. You say, okay, tomorrow I expect this, and so this unit has to come online at a certain time. This has to stay in backup and so on. So that's a feed forward planning. And then we have the feedback control. The classical one is, of course, to maintain, for instance, the frequency, where generation and load have to stay in tune all the time. Now, the objective of this project is to merge these two worlds, to allow for a better control of distribution grids. If you want to know more about this project, please contact me and I will forward you to the PhD and to the professor, because they know much more about this than I do. Now, let me again show this picture and just briefly show you how I map those three examples on this ReMaP platform. So you have seen this before. The case number one was a CHP plant. There was a simulated thermal storage. There was a demand from the archive, and there was a relatively simple controller sitting in the simulation framework. So that was the first time when those components really work together. The example that we are doing now with PSI, we will have a fuel cell electrolyzer on the EASY platform, the battery at eHub. The H2 storage will be simulated in demand, and again, a controller will reside in the simulation framework. And the last example that I showed is simply a new controller. So that's exactly this category here, where a new controller is being developed, which later on may be used in the context of the first example or the second example. It doesn't really matter, or in new examples that we are going to construct within ReMaP or within Pathfinder or within other suite projects in the future. So just a few more things on the link to Pathfinder. I'm following here now the structure that Lea has suggested. The linkage to other tools is what I showed you. ReMaP is not simply an energy hub simulation tool because it has this interface to the hardware. But still, there's a lot of data which can be exchanged. In exchange, I mean, it's a two-way exchange. So it's data that we have in ReMaP can be used by others, but we can also use demand and supply data, especially from the other simulation tools like Nexus E, Expanse, FlexEco, Calliope, those tools which are within the Pathfinder project. So that's a link to the other tools, really. The limitations, it's maybe not really a very strong limitation at the moment, but the current setup does not foresee time resolution in the sub-second range. I'm not sure. I don't think that's a limitation really for the Pathfinder project. So areas of power quality really in the millisecond region, that's not where ReMaP is really playing in. And of course, it's maybe a kind of trivial statement, but it's, at least on the hardware side, is limited to the available hardware, but which also means that within ReMaP now, as it runs now, and within Pathfinder, we have to see whether we can actually invest into new hardware. So possibly we have to work with what we have, but of course there are new partners with which we can come in contact, which have hardware, which then we can simply link via the software that was developed within the ReMaP platform. Now, spatial and temporal resolution. The spatial coverage is not really applicable here. When Marius showed something about Nexus, this would probably be Switzerland or Europe or whatever. I think you understood that that's not really what I'm talking about here for ReMaP. The spatial resolution is, well, generally we look at the multi-energy system at a district level. So that is the scope in which we are. Temporal coverage, now in the sense of the decades, it again doesn't really apply too much to this here. We will use boundary conditions which are defined by scenarios, and if these are net zero scenarios pointing into the future, then this will be taken then from for the future. Temporal resolution, as I said already, it's larger than seconds. But it's of course considerably smaller than what typical energy system models like Nexus, I guess, or like Calliope, at least as I know it. They usually have an hourly time resolution. Here we talk about second time resolution because we want to get into those real life control problems. Sector coverage, simple answer is everything that we plug in. So basically, it's the full energy system modeling this electricity, heat, and mobility. Mobility, especially now via EV charging, where we also have a hardware component, the Move platform at EMPA in the eHub framework. The users, the current users, are various investigators at ETH Zurich, EMPA, and PSI. So that is the user basis at the moment of the ReMaP project. The potential users are obviously all researchers within Pathfinder. I also put here DecarboCH, which is another suite project, and I should have put also Edge, which is the third suite project, which may want to use this platform. Utilities, industrial partners, we will have to find this out together, whom we can really serve with this here. Now, within the Pathfinder project, this is a graph showing the various work packages within the Pathfinder project. And I marked those where ReMaP is planned to play a role, but very simply, it's a two-step approach, really. Pathfinder is about finding transition pathways towards a sustainable net zero energy system of the future. During this analysis, critical issues will come up. For instance, the control of a distribution grid, whatever. So these are the critical issues. Those critical issues we want to look at in ReMaP. First, to be used as a simulation platform, building those digital twins that I spoke about a few times during my talk, later transition to a partial or a full hardware-based experiment. And then afterwards, we can go to a real pilot and demonstration project, which may again use certain elements, certain software components that we already developed within ReMaP. Maybe the controller is moved directly as a software from the ReMaP platform to the real life. This we will have to see. So that's a way how ReMaP shall interact with the Pathfinder project. So that was what I wanted to show you in those 20 to 30 minutes. I'm very enthusiastic about the project, I must say, because what I did in the past was I was always living in this energy system simulation world with hourly time scales, and everything looked smooth and nice at the end. But in reality, there's all those control problems. There's all those real life problems of voltages fluctuating and so on, which you completely neglect at in this world, in this level. And that's exactly what we are looking at in ReMaP, which I'm looking forward to further explore with ReMaP and with the Pathfinder project in the next 6 years to come. So thank you. This was my short overview, and I'm happy to take your questions, to have a discussion.